So my project for the Succinct Residency is a fast syncing Celestia consensus light client. I'm Connor. I'm a solutions engineer for Celestia. Usually I work on integrations with rollup frameworks, but in this case I'll be presenting on a research prototype. So at Celestia, we're this layer 1 blockchain that is very lightweight and scalable, and it has a version of the node that is light enough for anyone to run, and this is the Celestia Light node. It's been run all over the world on all kinds of devices, and it's a pretty convenient way for a user to use the chain without needing to delegate trust to an intermediary, which is a very important part of the goals of cryptocurrency systems. We already have an in-browser version of the Light node, which you could run by going to lumina.rs, but you'll find that's a little bit heavy, takes a little bit of a long time to synchronize, and so the problem that I looked into solving was to improve the experience of that and have something that synchronizes faster. The reason why it's so slow to synchronize a node of any kind, even a Light node, is because the headers are pretty big. With all the signature data that's needed to verify them, that adds up to about 70 kilobytes per header. But after you verify it, you can just delete it. So it's the kind of thing that you can save bandwidth by compressing using a zero-knowledge proof. So if you validate a header and you create a ZK proof of that, and you go all the way down to Groth16, which is the smallest kind of ZK proof that SP1 can give you, you end up with 300 bytes, which is quite a bit less than the 70 kilobytes. And when you have a giant chain of blocks, it really adds up. So we can just take a chain of these 300 byte proofs and verify that instead, right? No, we can actually do something a lot cooler than that. So when you create a proof of one header, you can feed that proof into the input to the proof for the next header. And what you end up with is a single 300 byte proof, not just for one block, but for the entire chain. And if you go to this website, you can actually sync the entire Celestia chain using my demo. And this is, you'll find that it is imperceptibly fast. You won't even understand what you're looking at because it's just, you just see a check mark and a block hash and you're good. So I'll leave that up for another second. And the idea is not, oh, sorry, okay. And come find me if the demo doesn't work, because it's been working, but I haven't tried all of your kinds of devices. So. Good to move on? Okay. So the idea is not new. It's been used on a few other blockchains in the past, notably by Celo, who had this Plumo project, which does a recursive consensus history sync, and by Mina, who also proves the execution of the chain itself as well. So it looks a bit like this. We generate proofs. We take the current block, create a proof for the current block, and then wrap it into the next. The code is on my GitHub, so you can take a look at it and try it out. This is a screenshot of the first time I tried to build this at the beginning of the year, where the proof time was 15 minutes. Now the proof time is only about 30 seconds because of improvements done by SP1. SP1 has given us ease of development. It would have been much harder to build this using a handwritten circuit. Instead, we're able to use existing Rust code. It has really good performance for Tendermint. We already have that deployed as part of the Blobstream bridge, which you might have seen or used before. And SP1 has a really nice recursion functionality. We took the SP1 snark verifier code and built it and compiled it into WASM to make this demo. So I think we may have done the first ever SP1 proof verified in browser. We took advantage of the ED25519 and SHA-256 precompiles, the recursion feature, and we use the prover network in production to constantly update the proof with the latest head. One iteration is 13 million cycles, and that's about 30 seconds when you're getting the full juice of the infrastructure. It's missing a few important features that we would like to have, one of which is validating execution. So that's to actually have this thing give you the same level of security that a full node, a blockchain full node gives you, we need to have the VM snarked as well. We also validate data availability, which is this third thing that a node needs to validate in order to be trust minimized. And right now in our current implementation, it's a little bit too bandwidth intensive to be unnoticeably light. But there is research being done that we think will help us lower the footprint for bandwidth. Also, you might have noticed that the proof time is slower than the block time. That can be fixed if you upgrade the cryptography to support accumulation somehow, which is a cool thing that the cryptographers will know about. Anyway, that's all.
Great, thank you so much, Connor.